Fingers crossed. Okay, right, so I'm going to talk about splashing, sloshing and stealth, offshore hydrodynamics writ large, and this is work that's been going on in Oxford for about the last 20 years or so. I'm going to talk particularly about the interaction of large tropical storm waves with large offshore structures, with an Australian theme, because Lionel asked me to mention Australia, but actually this work has got quite strong Australian connections. So splashing for tension leg platforms and semi-submersibles, sloshing in the gaps between large vessels, and stealth, how one particular platform can move but doesn't make any waves, which is quite fun. I've got some acknowledgements I'd like to make. I've had the pleasure of having two fantastic colleagues working with me in the same research group since I've been here, Rodney Taylor and Alistair Borthwick. Rodney's sadly for me anyway, retired, and Alistair Borthwick's moved on to Edinburgh, but they've been fantastic colleagues over the years. And then the people who do all the work, of course. A whole group of extremely good research assistants and graduate students who really are responsible for what I'm going to talk about today. And then industrial collaboration with both BP and Shell particularly, and sponsorship from whoever will basically give me money. Right, so this is just a picture to set the scene. This is obviously a world map showing the paths of severe tropical storms over about 150 years. So hurricanes in the Western Atlantic, some of them going into the Gulf of Mexico, taking platforms out there. Hurricanes offshore Mexico and California, super typhoons in the Western Pacific, particularly clobbering Philippines, as we know. We've seen on the news fairly regularly. Taiwan, Japan, and so on affected. And then in the southern hemisphere, the north coast of Australia regularly hit by what they call cyclones. We zoom a little bit into Australia. Those are all the cyclone paths over 36 years. And an awful lot, Queensland across to Western Australia, with Darwin in the middle, which got taken out by a cyclone, what, 50 years ago? Darwin, something like that? Yeah. Something like that. Anyway, the reason why this map's particularly interesting if you're interested in offshore engineering is there's a large number of developments up here, offshore. So Australia gets hit by large cyclones. Here's one out over the Indian Ocean and another one forming off Queensland. And then picture of Northern Australia, actually with three cyclones simultaneously. You can see the eye of each of them. So tracking from east to west. Very, very large storms. A large-scale cyclone is the same as a typhoon, is the same as a hurricane. The only difference is in the southern hemisphere they rotate in the opposite sense. But strong interaction between the atmosphere and the ocean, all driven by hot water, effectively. It's a thermodynamic heat engine. Okay, so this is the trajectory of one cyclone in 1995, came over Darwin, tracked along the coast all the way down before going onshore near Exmouth and Barrow Island. The reason why the Australians, and I guess the oil companies as well, are particularly interested in cyclones is, this is the north coast of Australia. You can see the locations of interest for oil and gas exploration and production. Basically along the line of the hurricane, of the cyclone tracks. So we're interested in interaction of big offshore structures with even bigger waves. One thing I only discovered yesterday when I was researching this lecture, the highest wind speed ever recorded by an anemometer is at Barrow Island. 250 miles per hour. I had assumed it was in the Western Pacific where they get super typhoons. Well, maybe they get up to 240 miles an hour there. But we are talking about really the most severe storms on the Earth. Of course, for cyclones and hurricanes, waves aren't the only problem. Storm surge floods inshore, and it rains. And it seriously rains. So clearly, under there somewhere is a road. Well, we guess anyway. In the UK, we're interested also in waves at the coast. And most of you will recognise the seafront of Dawlish well, what's that? Washing a train, washing the track away. And it took, was it 3 months to rebuild it? So that Cornwall was being cut off essentially from the rest of the UK for about a 3-month period till they rebuilt the railway. This is a storm off the, in Scotland, large storm going inshore, flooding a town. So the interaction of very large waves, both offshore and as they come into the coast, is clearly of engineering interest. Okay, how about some direct Australian connections? Well, the first thing is that UWA has a particularly attractive campus on the edge of the Swan River. I thoroughly recommend it, and the weather is very nice as well. But there are strong connections between civil engineering and particularly offshore engineering and UWA, and it tends to have been, it's not really an exchange of people. We send them out, they seem not to send many people back. When I first arrived, Mark Cassidy was here as a grad student, supervised by Guy Horsby and Rodney Taylor, and I helped Mark a little bit with some wave modelling on jack-ups, and he's now a full professor and director of the Centre of Offshore, what do they call it, Offshore Foundations. More recently, we've had two very, very good grad students in Oxford, Scott Draper, who worked for Guy and Alistair Borthwick, and Scott had the misfortune to have me as his internal examiner, but he lived to tell the tale, so I guess that was all right. Slightly after Scott, we had Hugh Walmagott, Australian, now gone back to Western Australia. He came on a Clarendon scholarship, and we were very pleased to take him because we trumped Stanford. He also had a scholarship offered by Stanford University, and he decided to come to Oxford instead. I hope he doesn't regret the choice. I don't think he does. And the final connection that I have is Wensong Zhang, who was an Oxford MPhil student, or MN student, 2 years ago, did his final year project supervised by myself and Richard Darton on a sort of combined mechanical chemical engineering project. And he sort of closed the loop because he's gone off to Australia and he's now one of Mark's graduate students, which is quite a nice circle, I think. But what I want to really talk about in my talk is splashing and sloshing. This turns out to be very important for the Australian oil and gas offshore developments off the Northwest Shelf. And there's considerable interest in what we're doing and collaboration developing with these guys out in Australia at UWA and also the offshore operators in Australia. So let's put a big wave past the structure. So this is shots on a wave-by-wave basis on Oseberg A, which is a concrete platform offshore Norway. You can see behind the platform, well, there are some waves. The wave heights there are maybe 8-10 meters, trough to crest. Here's when the wave trough interacts with the four legs of the platform. Here's the wave crest. Somehow we've converted an 8-meter wave into a 25-meter up and down motion locally. Local, very strong interaction between waves scattered off these individual legs, building up essentially a standing wave pattern below the platform. And over the years, we've made fantastic use of Rodney's diffract code to do wave structure interaction. Well, in fact, it does the diffraction part, hence its name, the linear and non-linear diffraction. And most of the results I'm going to show you are produced with that code, which has obviously gone through several iterations over the years. So we're talking about big bits of kit. Here's two tension leg platforms in the Gulf of Mexico, a concrete semi-submersible. Yes, concrete will float if you give it enough buoyancy. Off Norway, BP's Thunder Horse platform being transported out into the Gulf of Mexico, and a big floater offshore Brazil. Each of these is probably $3 to $5 billion. So we're not talking about small amounts of money if an oil company invests in one of these, and they don't want downtime. They don't want even minor structural damage when it gets hit by a big storm. But damage does occur. So this is a flotel, an accommodation platform used in the used in the North Sea. And last winter they had damage to the lifeboats, which are here and here, which meant they had to withdraw it from service to fix it for 3 months. Rental rates of these sort of rigs, a couple of $100,000 a day. So we're talking about serious amounts of money to take it away, repair it, and send it back in place. So let's see a simulation of a large wave interacting with the structure. So here's a fixed platform with 4 legs. The waves are coming diagonally in from the left. And red is bad. That's all you need to know about the movie. Red means the wave has hit the deck, which is obviously not shown in the cartoon. So outside the platform, the wave amplitude is 12 meters. Below the deck of the platform, it goes up to about 24 in the movie. Very dramatic amplification. And it's just a single transient wave packet. Produces this very, very high elevation. And if you do similar simulations in a random sea, the longer you wait, the bigger the wave gets. So this is a simulation in a typical, maybe 1 in 5 year winter storm out in the North Sea for that previous platform geometry. So all the waves produce very small responses. A 1 in 1,000 wave produces a response over here, and a 1 in 100,000 wave is over here. So the wave heights in the open, crest elevations in the open ocean and you get roughly 1,000 waves in a decent storm, at this sort of level is water up to maybe plus 12, plus 13 meters compared to mean sea level. If you put the platform in and you account for just linear diffraction, it goes up to about 16 meters. You account for second order as well, it goes up to, in this case, about 22. So that's fine unless the deck of the platform is here, in which case there's, what's that? That's about 4 meters of water up at the deck. And that's a typical large wave within a severe winter storm. If I look at the probability out at the 1% level, so there's a 1% probability of getting a wave this big in this storm. The undisturbed wave has grown to about 15 meters. The interaction with the structure goes up to 27. So it's very, very strong nonlinear effects. And with a deck at 17 meters, you're in serious trouble. So that's kind of interesting. Fortunately, people wouldn't design a 4-leg platform for the Gulf of Mexico, for the northern North Sea with a 17-meter air gap. They give it more like a 25-meter air gap for obvious reasons. But what we've been able to do with our work is come up with what you could call a designer wave. So this is the time history of the most probable maximum response in that sea state at the 10 to the minus 3 level. The water at time 0 gets up to 22 meters. And that is consisting of some linear amplification of the green curve, plus the red curve making the 22 or so. The incoming wave field that produces 22-meter interaction with the structure is only about 10 meters high. So there is this magnification by something like 2.5. So that's for a fixed structure, but a lot of structures offshore float. So here's a simulation of the same platform, but floating. And you can see it moving left and right, and also it moves vertically. Again, red is bad. And the color coding is relative to the deck. So we don't want any red within the platform cross-section between the legs. So you can clearly see here there's a lot less red color. The motion of the platform as a big wave goes through, the whole platform moves upwards a little bit, which amplifies your air gap, means it's much less likely to get waves in the deck. Oops. Okay, so to look at the statistics of that same geometry, but one freely floating, the other fixed. Here's the fixed results. Relative air gap now at the 1% level. The deck just about gets touched by the wave crest. So that won't do structural damage. Somewhere up here would do significant structural damage. So this is an interesting result. These are new calculations, and hopefully they will be picked up by the offshore industry. Just some very brief conclusions. Significant interactions, magnifications of something like 2.5 times. Doesn't matter what shape the legs are, doesn't matter whether they're circular or square, as long as they're just large volume legs in close proximity. If you restrain your platform vertically, as tension leg platforms are restrained, you just need to build in bigger air gap, which costs you more money. Freely floating model is harder to operate as an oil rig, needs catenary mooring systems and so on, but you'll get less deck leg impacts, or you can simply afford a lower air gap. And we've come up with a designer wave. So that's splashing. Now sloshing. Lots of interest in Australia in floating, in production of liquid natural gas from floating facilities. So this is Shell's Prelude design for a floating LNG plant. I think it's the world's biggest ship at the moment. It's 450 odd meters long. The idea being this is moored in place above the gas field. The gas is produced up into this platform or this floating body, which then liquefies it, sticks it in a shuttle tanker, and then you sail the shuttle tanker off to Japan and sell them liquid natural gas. Very, very important economic way of developing what are called stranded gas fields where there isn't anywhere to build a pipeline to supply within a reasonable economic distance. So you can exploit the gas fields off the north coast of Australia with this route, which is what Shell is trying to do. But nasty things do happen in gaps. I've just stolen a little bit of video from a company who will do ship-to-ship transfer for you. So this is, these are not LNG tankers, these are just two oil tankers. You see waves sloshing in the gap. Very, very violent interactions. When the sea state outside, you'd hardly notice any waves at all. This becomes an issue, of course, when the wave crests reach the deck. Then you start to flood the deck and you're in danger of damaging equipment. Okay, so enough of that. So this is, again, Shell's Prelude platform with a shuttle tanker attached to it. And this is a very difficult problem to do diffraction analysis for because you've got a vessel that's 450 meters long and a 4-meter gap to another vessel 300 meters long. It's extremely long, thin geometry. It's very difficult to do robust analysis for. But fortunately, Rodney's code diffract will do this. And this is a simulation. These are the peak surface elevations of waves coming in broadside onto the far side of this big structure, so that you get an amplification of about 2 because the waves hitting the broadside think they're hitting a vertical cliff. Around the lee side of the shuttle tanker, there's hardly any waves at all, but you get a magnification of 6 times in the gap, 6 times the size of the incident waves. So if the incident wave is 2 meters high, you get 12 meters in the gap, and when the shuttle tanker is fully loaded, the freeboard there is probably less than 12 meters. So there are economic issues, safe operating issues associated with these sloshing phenomena. You don't only get 1/2 sine wave, you can get all sorts of other shapes. Oops. Yeah, it's playing. Again, broadside, all you're seeing is the water, and you can see we've now got 3 wavelengths in the gap, sloshing, and much larger elevation in the gap than anywhere around the structures away from the gap. So an interesting example of potential flow hydrodynamics producing very, very violent local amplifications. And I just point out that something like this, I mean, Shell have not announced what the final costs will be. It's 12 billion and counting so far. Should go in place either next year or the year after. Should start production in 2017 or so. Stay in place for 25 years. All dependent on what goes on in the gap between this and the shuttle tankers. Okay, so that's the second topic, sloshing, now stealth. And I am going to show a picture of an aeroplane in a minute, so the enthusiasts in the first lecture will be no doubt pleased. I'm talking about a structure which can move, will move, but will generate no waves. And this is the structure we came up with. It's a ring of 8 simple vertical cylinders, which have, if I can find my prop, oops, I don't know if you can see it, a hemispherical end cap, which is actually from a snow globe, from a manufacturer who makes globes for snow globes. And we had to size the hemisphere before we could size the tube, because hemispheres are much more difficult to find. Anyway, that's the ring of 8, and you'll see it move in the Coast Lab in Plymouth in a moment. But how did we come up with this? Well, we were trying to do something more useful. We were working, in fact, Hugh Walmagott, who's now at UWA, was working on the interaction of arrays of optimized wave energy absorbers. So for marine renewable energy, wave power systems. He came up with a theorem. I think this is the one and only time I've come up with a theorem that's actually any use to anybody. He came up with the following result. Averaged over all approach directions, an array of devices can only absorb the same energy as the sum of the devices all acting in isolation in the same wave field. And that's an integral property. There's a formal mathematical proof which we've published, and we can also test our diffraction calculations with it, and that's what's done down here. So Hugh invented a completely crazy wave power array of 3 different shaped bodies, an ellipsoid that's going to heave, a hemisphere that's going to surge, move along the wave propagation direction, and an elliptical cylinder which is going to sway transverse to the mean wave direction. And so in the plan view, this is his lunatic design for a wave power system, and an approach angle of 0 here, going all the way around the clock back to 360. And this is how much power you take out in a given direction. So that if we look at, for example, quite long waves, clearly there are preferential directions, and the directions which are very unpreferential, very deleterious to taking power out. The interactions, the directional effects are stronger the shorter the waves. So if we go to quite short waves, there's a direction where you can capture twice as much energy as average. You think that would be great. But if the waves come at a different angle, you capture 35% of the average. And the whole point about this is if you integrate it over all possible directions, the answer must be 1, which is what the theorem says. So when Hugh ran diffract on this problem, we integrated around, it turns out to be 1 to about 10 to about 4 significant figures, which is a very, very good test of diffract, Rodney's code. And as a consequence of that, this paper is getting quite a lot of citations now, although it's a piece of applied mathematics, because there are lots of people working in wave power systems, working on arrays. And if you put 100 floats in, you don't want to have to study the precise interaction of every float with every other float. You want an approximate technique for designing your array. Well, this integral result is a way of testing the accuracy of your approximations, which I think is why it's quite a useful result. So we got into looking at the interaction of multiple bodies, including what turned out to be the ring of 8. So 8 vertical cylinders, freely floating in heave motion, vertical motion in and out of the water. What is their behavior if you treat them as a solid body? Well, one of the things we looked at was how efficient they are at radiating waves outwards. So converting the structural motion vertically into wave energy radiated to infinity. The reason that's interesting is that if you run the system backwards, you have energy coming into infinity, which the system absorbs. So that's a wave power system. So as a function of frequency, more particularly frequency squared, this is the radiation damping as a function of frequency. So there's a slow decay as the frequency goes up. There's one particular frequency at which the wave damping drops by a factor of 1 million. Doesn't go down to 0, so the mathematicians won't allow me to call this a motion trap mode. It has to be a near motion trap mode. Mathematicians can tell the difference between 10 to the minus 6 and 0. An engineer can't. Okay, so the odd thing about this is that this is not a particularly special structure. All the other structures that feature trapping have strange shapes when they penetrate the surface. They certainly, for this problem, would have cylindrical symmetry, because this one is not cylindrically symmetric, because it's got 8 rather than an infinite number of legs. So there's my stealth aeroplane, just to show willing. What I'm talking about is free surface motion in the vicinity of a body where that motion does not go out, the fluid motion does not go out to infinity, does not take any energy away from the motion. Over, I guess, the last couple of decades, there's been quite a lot of work in water wave theory on what are called sloshing trap modes, where the body is stationary, but the water just goes up and down around it. Only a few years ago was it discovered you could have what are called motion trap modes, where as the water moves, the body moves in the opposite direction, essentially. So what we were interested in is a problem where you have 0 radiation damping, so no loss of any vibration out to infinity, but at the same frequency, the body can move freely. This is free heaving mode. So this is these are the 2 equations in my presentation: no damping and a mass spring damper to set the resonant frequency. So I hope that's acceptable. The key thing is that although there is theory based on this, or rather complicated geometric shapes, nobody's ever done an experiment. So we thought we'd do an experiment and see if it actually works. The other reason why it's of interest is that the internal mode, where you have the body moving and the water moving in antiphase, cannot be excited by an incident wave. If an incident wave comes in, the body is essentially invisible, so it is actually a stealth mode. Okay, so what does this motion look like? Well, this is the theoretical prediction. Here's a ring of 8, cross-section of each of the cylinders. As the cylinders move into the board 1 unit distance, they displace water, which produces a hill. This is the hill. The hill has a maximum displacement of about 0.45, and the water motion is entirely restricted within the ring. There is nothing going on outside. So that's a theoretical prediction from the diffraction code. I just want to stress what a remarkable result that is, because almost any motion you do close to a free surface makes waves. And if we have any punters in the audience, they've probably seen pond skaters out on the Thames. Very, very small motions of their legs produce really quite large waves, and that's how they talk to each other. And they can not like each other, they can like each other, it depends on how fast they wiggle their legs. The point is that what we're describing is free surface body motion and motion of the water without any wave radiation. So none of this stuff. So let's see whether it actually works. I thought I'd put up this picture just to prove that although I'm a theoretical engineer, I do very occasionally get my feet wet. So this is the model about to go in the tank. This is Colin Whitaker, who's actually New Zealander, not Australian, sorry. Near miss as far as the English are concerned. This is Alison Braby, who's now a reader at Plymouth University. She's an ex-student of Alistair Borthwick and mine here. So this is very much keeping it in the Oxford family. This is a simulation, or meant to be a simulation. Yeah, okay, so on the left, the tuned model, on the right, the detuned model. You can see all the wave radiation if the geometry is wrong. And the energy is lost from the system, so the motion stops. Here, the energy is confined, the motion just keeps on going. Kind of fun, theoretical prediction based on a code written by Colin here. That's the predicted motion, allowing for wave radiation when the system is detuned. When the system is tuned, very nice radiation, no radiation at all. Let's see if it works. Let's see if the movie works as well. So here's a detuned case. About 5 cycles and then the motion stops. So that clearly, that motion, that initial motion is making quite large waves and losing lots of energy. Okay, the tuned one. Free vibration, just keeps on going. Does eventually damp out, but clearly very, very dramatic difference. If one looks at those results, here's the one which is detuned, decays very quickly. Most of the energy is lost by wave radiation. Here's the tuned case, small loss in amplitude. That's viscous boundary layers. That's real fluid mechanics, not potential flow. But we've calculated how much that should be based on Stokes oscillatory boundary layers, and the decay rate is right. So that's a nice modelling result. So we're the first people to observe near motion trapping experimentally, near brackets 1/1,000th, with a small viscous decay rate, very low radiation from what's actually a very simple geometry, an unremarkable, unspecial geometry. So I think at that point I should probably stop and say thank you very much, and I'm happy to answer any questions.